We are entirely used to seeing Christ the Redeemer as a still, peaceful icon watching over Rio de Janeiro, but the extreme geography of its isolated location suggests that a 1,000-ton structure shouldn't even be able to stand here. This is Mount Corcovado in 1890. It is an isolated granite spire plunging straight into the rainforest, 700 meters above the ocean. This peak sits directly in the path of violent Atlantic storms that hit the summit with relentless winds exceeding 200 kilometers per hour. Placing a massive monument on this needle meant managing a construction site with zero storage space. Because the climate shifts every 10 minutes, materials had to be poured or assembled the same day they arrived, often while visibility dropped to absolute zero. Choosing the Hunchback Mountain as the site for Brazil's centenary monument turned a simple commemorative project into a brutal, all-out engineering offensive against the forces of gravity and the relentless Atlantic winds. When engineer Heitor da Silva Costa won the project in 1921, his initial sketch featured Christ holding a giant cross and a globe. The public mocked it as Christ with the ball. Silva Costa responded by designing an Art Deco cross, where the statue's body and arms formed the monument's core. This diagram shows the technical crisis that design created. The 28-meter outstretched arms form a massive surface area that acts like an enormous sail. During hurricanes, the crosswinds exert hundreds of kilos of pressure against every square meter of the structure. By prioritizing this modern silhouette, the team introduced structural stresses that standard 1920s masonry couldn't withstand. Many experts argued for a steel skeleton, similar to the Eiffel Tower. But Silva Costa knew that exposed steel, hit by Rio's salty ocean air, would corrode and require unsustainable maintenance within a few decades. He chose reinforced concrete instead, a material known then as the artificial stone of the future. To prove it could work at this scale, he hired structural engineer Albert Coco to calculate the specific tolerances needed to survive a hurricane. This heat map illustrates Coco's solution. He designed an internal skeleton of diagonal pillars and beams that remain rigid under pressure. This geometry forces the lateral push of the wind and the weight of the concrete straight down into the mountain's granite foundations. The statue stays upright because of these invisible mathematical calculations, which function as a structural shield beneath the surface. Getting the materials to the peak required a synchronized logistical loop. There were no paved roads leading to the summit in 1926, so every bag of cement and gallon of water traveled up the mountain on the small wagons of this rack railway. The aesthetic components travels even further. Sculptor Paul Landowski created full-scale plaster models in Paris. These were sectioned into numbered blocks, shipped across the Atlantic, and reassembled atop the mountain like a three-dimensional puzzle. Workers lived in extreme isolation, operating without modern safety harnesses. They spent their days balanced on slippery scaffolding within the clouds, pouring concrete at heights where a misalignment of a few millimeters at the base would result in a meter of error at the summit. Despite the exposure shown here at the base of the pedestal, 9 years of construction passed without a single recorded fatality. At a time when safety standards were minimal, the project set a rare technical safety record. Success depended on a precision schedule. By turning the rack railway into the project's only artery, the team maintained a constant flow of material that outpaced the mountain's natural defenses. Concrete has a known weakness. It cracks under thermal stress. To protect the core from the Brazilian sun and moisture, Silva Costa needed a waterproof skin. He chose soapstone, cutting it into 6 million small triangles. Local women glued these onto linen sheets to create a mineral wallpaper. On the back of these stones, they often wrote the names of family members, sealing thousands of personal messages into the monument's exterior. This X-ray reveals the monument's internal architecture, a 12-story hollow building. A metal staircase weaves through reinforced concrete levels, allowing engineers to climb from the feet into the arms and head for inspections. This hollow design sheds enough weight to keep the load manageable for the granite foundation, while giving maintenance crews a permanent internal path to every structural joint. Today, the mountain continues to attack. As the highest point on an isolated peak, the statue is a constant target for violent electrical discharges. To prevent the concrete from exploding on impact, the internal steel framework functions as a Faraday cage. Lightning rods in the head and fingers channel millions of volts through the metal armor and into the granite foundation. The internal skeleton is a dual-purpose system. It carries the physical weight of the 1,145-ton monument while neutralizing atmospheric electricity. In 2014, a strike vaporized the soapstone on the statue's right thumb. Repairs required specialized climbers to rappel from the head and walk along the arms into the void, reconstructing the tip with stone from the original 1930s quarry. When the floodlights were first activated on October 12, 1931, the crowd saw more than an icon. They saw the result of calculated risks. Beneath its stone skin, Christ the Redeemer remains a warrior of reinforced concrete. It stands as a testament to the technical precision